In problem 13, 65, you have a 250 gram mass that's mounted on a spring. It gives a spring constant, and it has a damping constant. And so this is damped harmonic motion. And what it wants to know is how many oscillations will this system undergo before the amplitude of the vibration decreases to 1 over E of the original value. So we can visualize this motion in terms of an amplitude that varies with time, so that as the spring vibrates, the amplitude decreases ultimately over elapsed time to 1 over E, A times e to the minus 1 of its original value. The given constants are the mass, the spring constant, and the damping constant. And the fact that at some given time t, where the amplitude now is the original amplitude reduced by a factor of E, what is the number of vibrations that this will go through? So we'll have to determine the elapsed time. And then if we can find the period, then we can probably find out what this constant is. Now we go back to the original equation in terms of a amplitude which decreases as a function of time. So the displacement in the x direction is the amplitude times the cosine of the frequency of vibration times the time plus the phase factor. Now the only thing we really need to be concerned with is how this amplitude changes with time. And if we have damped motion, then the amplitude is equal to the initial amplitude times the exponential raised to the minus damping constant times t over 2m. The frequency of vibration, omega, is the square root of the spring constant over the mass. Those are given. And to find this number of oscillations, we'd have to take the elapsed time and divide by the length of the period, and we'll find the number of periods this went through, or the number of vibrations. Of course, the solution is to take the amplitude as a function of time. Here it is, and then set that equal to the amplitude at the known time, or the time that we're interested in, and simply solve for the time. So here you can see this exponent must be equal to this exponent, so that minus bt over 2m equals minus 1, or you can solve for the time, and that's 2m over b. 1 over the period is the angular frequency divided by 2 pi. And so that's omega is the square root of k over m. If you divide that by 2 pi, then you've got 1 over t. And n is the product of t and 1 over t. So if you multiply this term by this term right here, you'll find the number of oscillations. When you plug in your numbers, you'll come out with a value that's not an integer. But if you'll round this off to the nearest integer, then you'll have the number of vibrations that this has to go through.